Thank you. Thank you, everybody. So this talk today, the time we have allotted is to 12:30. I'm going to try and give an hour talk. That's always a challenge. But anytime you have a question, please don't hesitate to raise your hand, because why wait? And then this afternoon there's another question and answer session from 2 to 3. And the talk today is partly to this question, really in a kind of a sandwich. The bread is context, so I'm going to start off with a little context for thinking about problems like this and questions like this. I'll have a bunch of examples in the middle, and I'll finish with a bit more context. Those finishing things are designed so I can stop when the time becomes available. So each one of them is a potential stopping place. And the other thing is, should mention, is a couple of days ago I got given a bunch of questions that came out of one of your sessions, I guess on Monday. I found them very useful. Probably most of the answers to those questions might be done this afternoon, but please don't hesitate to ask any of those questions here and now. So, of course, lines of code is not a great way of measuring anything. On the other hand, it's something people have to write or get a computer program to write lines of code for them. So I thought I'd at least start off with a metric here and point out that a 400-page book has about 20,000 lines of something in it, about 50 lines a page or so. And so a foot of books is about 300,000 lines, and a meter is wonderful because it's about 1 million lines of code of stacked books. So it's worthwhile thinking about 1 million lines of code from that standpoint, because it's on the order of just 50 books, and most people don't read 50 books in a year. Right? In fact, the average number of books read in a year by people who read at all is about 10. So even 1 million lines of code has probably not been very carefully looked at by anybody. It's rather more dipped into like the Bible. People rarely read the Bible sequentially. They instead find there's some frisson in their life, and they dip into the proper part of the Bible to make them feel better. And that's sort of what happens in code. It's actually part of a religious... Bob Barton once pointed out that computing should be in the school of religion, and he once called systems programmers high priests of a low cult. So if you think about it, what happens is something goes wrong, and we tend to dip into the Holy Scriptures to try and find the place that will resonate with what's wrong, and maybe will help us fix it. So now the problem is that our actual measurement for code these days is something more like the Empire State Building, which in terms of stacked books is 22,000, as you see there, and about 400 million lines of code. And that sounds outrageous, 22,000 books, 400 million lines of code, but in fact there's a lot of software today. Many companies are maintaining more than 400 million lines of code. So we're talking about sizes of code that are simply enormous. For example, even humble personal computing, as done by Microsoft, is probably at least 220 million lines of code just for the operating system and for Microsoft Office. So that's a lot of code. In fact, one of my favorite things about Microsoft Word, besides the fact that the original version was done at Xerox PARC in 1974, is that in today's Microsoft Word, there's a bug that's been there since the 80s, and it's a visible bug. You can experience that bug by setting global hyphenation on and selecting things around, doing editing, and about every 10th selection, when you type, the typing will not go into the selection. It'll go a few characters to the side. Anybody experience that bug? been complained about for 30 years. Microsoft cannot find that bug. It's not that they haven't been tried. It's been complained about by thousands and thousands of people, and it's a visible bug. It's not like all the invisible bugs that Microsoft puts out. So I'm just pointing out there's a problem, and just to complete the 400 million line idea, there is at least one large financial products company that I'm aware of that has more than 400 million lines of code, 170,000 screens in their user interface. A company that uses the term screens is one that has not advanced beyond the 3270 because that's the way things were thought about. No, but that was the nomenclature back then, and so they think about these things as individual presentations. They have to involve all of them. So today I'm just going to look at personal computing because it's something we're all familiar with, and the 1 hour talk today is kind of a distillation of a day-long workshop that I did with a large aerospace company a year ago. So they seemed to fit what was requested, and so I tried to peel down about 8 hours worth of stuff into an hour of questions and a few points, some of which will be nicely arguable. So here's the deal. We've got two terms. We've got complications, which I'm going to define as things that we do, sometimes called accidental complexity. People are trying to make it look better. But actually, a lot of the complications we put into code is not really that accidental. It comes from bad process. So you can't really call that accidental. And complexity is some intrinsic measure of what the meaning of the code is. And it's really hard to define because you don't want to define it in terms of Shannon's entropy measures, because that takes out of the equation the fact that you'd like whatever form of that code, the code is that's roughly at the level of complexity of what it's trying to describe, you'd like that to be human readable. So I'm just going to go with an informal way of looking at things. And basically what we've got here is we would like what we do in the red here to be very close to the intrinsic complexity. And what we've got, I think, is something that is more like this. We've got something where the amount of complication can be hundreds of times more than the complexity, maybe thousands of times more. This is why appealing to personal computing is, I think, a good ploy in a talk like this, because surely we don't think there's 120 million lines of code of content in Microsoft's Windows. Surely not. Or in Microsoft Office. It's just incomprehensible. And just speaking from the perspective of Xerox PARC, where we had to do this the first time with a much smaller group, and it's true there's more stuff today, but back then we were able to do the operating system, the programming language, the applications, and the user interface in about 10,000 lines of code. Now it's true that we were able to build our own computers. That makes a huge difference, because we didn't have to do the kinds of optimization that people do today, because we've got things back-asswards. Today we let Intel make processors that may or may not be good for anything. And then the programmer's job is to make Intel look good by making code that will actually somehow run on it. And if you think about that, it couldn't be stupider. It's completely backwards. And what you really want to do is to define your software system first and define it in the way that makes it most runnable, most comprehensible. And then you want to be able to build whatever hardware is needed and build it in a timely fashion to run that software. And of course that's possible today with field programmable gate arrays. It was possible in the 70s at Xerox PARC with microcode. The problem in between is we went, when we were doing this stuff at PARC, we went to Intel and Motorola pleading with them to put forms of microcode into the chips to allow customization of function for the different kinds of languages that we're going to have to run in the chips. And they said, what do you mean? What are you talking about? Because it never occurred to them. Still hasn't. So what about the Harvard architecture on the Intel chips? Well, it'd be great if the level 1 caches were big enough to hold an interpreter for a higher level language, but they aren't. So whatever those level 1 caches in there in the Harvard architecture, they are not for anything in particular having to do with what's going to be running on the computer. So there's a huge mismatch there. And some of the code that I'm complaining about actually has to be done. So I'm going to ignore that. I'm just going to ignore that and just concentrate on issues like this. And what I want to do is to look at this in a quasi-scientific way. And to do that, I have to say something about science. And to me, science is about hairballs. And this is my favorite hairball. It's about this big. It's from the stomach of a woolly mammoth who was found trapped in a glacier. So it's probably the largest hairball known. And now that I've got your attention, again, I'll go to the starry heavens. But it's the same deal. Starry heavens has been a hairball to humanity for hundreds of thousands of years. What the heck is it? What's going on? And all we get from nature is phenomena, because our brains aren't set up to get the truth directly from nature. We have to try and interpret phenomena, and we wonder, what does it all mean? And this is the Sheffer-Stroke, the NAND function, from which we can get all things having to do with languages and representations. And in examining the phenomena of light and other forms of radiation, we come up with a T-shirt that has Maxwell's equations on it. And the T-shirt can hold couldn't hold the form of Maxwell's equations that Maxwell put out, because he wrote in terms of Cartesian coordinates and in terms of partial differential equations. So it was up to people like Helmholtz, who devised the curl and divergence and gradient as essentially macro operators. What mathematicians call an operator is not what we call an operator. In this case, for instance, the divergence operator is something that represents, the gradient operator represents something like a bunch of partial differential equations from which you can translate this into. So this gives you a way of looking at it, and a little gander at it reveals that the electric field and the magnetic field are not symmetrically stated, and that, according to Maxwell, that can't possibly be, but there it is. So what does that mean? And a few years after this, by thinking about what that meant and a few other things, Einstein came up with the special theory of relativity, in which these things are symmetric. Okay, so what science is are these blue arrows. So science is not this. This is a story. And science is not the phenomena up there. Science is the relationship between the phenomena and the story. So it's actually not unlike the kinds of things we do in engineering with tolerance. Those blue arrows represent what you might call an error function or a tolerance function between the best we can do out there and the best we can do down here. This is very hard to explain to K through 8 teachers, because they've been taught that science is a new kind of religion in which there are just a new set of truths that have to be learned as a catechism, and it's their job to dispense the catechism. Okay, so that's part of it. On the other hand, so my misspent youth was partly spent in mathematics and also in biology. I have a degree in molecular biology. And in biology, there's also a T-shirt which has Schrödinger's wave equation on it. This is a nice small thing that gets rid of the PDEs also. Replaces it with a Hamiltonian. And there's no question that to the limits of what we actually understand about how things actually work at the what you might call the gear intermeshing level, it's all governed by Schrödinger's wave equation. When we do a 1,000,000 or 2,000,000 atom simulation, we get something that may reveal things that we didn't know about in nature, as Caltech did last year. And when they went looking in nature for the thing that was revealed by the simulation, by golly, there it was. And that's pretty darn neat. But try to think about those little green guys up there are water molecules. And that SpongeBob SquarePants thing in the middle there is a 5,000 atom protein. And that panel fits into the square up above where we see one end of one of the flagella. And that panel fits into that part of one of the smaller living things we know about, which has about 120 million large molecule components in it. And that's nothing because E. coli bacteria, about 1/2000th the volume of typical cells in our body, and we have 10 trillion of them. So a little bacterium on just a developing embryo fits into a tiny corner. So, forget about Schrödinger's wave equation. We've got something else that we need to think about what's going on in biology, and it's something more like a systems manual. There are systems aspects here, architectural aspects here, where knowing individual things about the bricks is almost irrelevant, almost completely irrelevant. What's really interesting is how do these things organize themselves without any central control to develop into very complex organisms, and to do it most of the time where virtually all of the zillions of errors that are committed during each and every morphogenesis of a living organism is canceled out by something. So this is something every computer scientist should know. And I don't know of a good book in computing to point you to, but this is an awfully good book. I recommend the third, even though there are more up-to-date versions of this, the third edition of Molecular Biology of the Cell is very, very revealing for anybody who's interested in systems. Well, and so then we think about when we're trying to deal with our complexity and complication problems, we probably need to use some sort of combination of math and something like biology to get the complications down in the kind of shouting distance of where the actual complexity is. And we should be able to do that because ours is a synthetic field. So we lack the fact that nature has already done it for us in biology. But on the other hand, biology is incredibly kludgy, unbelievably kludgy. It's one of the best arguments for evolution there is when you get into the details of how biochemistry actually works. And we get to design. We get to do the thing the creationists, I think, mistakenly think actually happens, where we get to do it, and so we should be able to design better than just making kludges that are thousands of times larger than they need to be. So if we carry this idea over to engineering, somebody can make a bridge up there, and that bridge, having been made, is phenomena. Doesn't matter how it got made. Once it's made, it's phenomena. We can get some scientists to come and make a T-shirt, and they do. And from that T-shirt, what's really cool in the 20th and 21st century is we can make one heck of a goddamn bridge. How big is this bridge? This is in Japan. That up there is a super tanker. So this bridge has, it's almost 2 miles of clear span there. Japan. There's the Empire State Building and the Great Pyramid of Egypt. Cool, huh? Let us all pause to give thanks that we live in the century in which the great art forms are the merging of science and engineering. The yin and yang came together, started coming together a couple hundred years ago, and man, I just get chills thinking about it. It's just like the greatest thing ever. And we're in this boat. So we not only need the t-shirt from the scientists, we need a zillion plans and organizations the equivalent of the molecular biology of the gene to make that actual bridge, as the Japanese did so well. Now, we can do this with computers. And this was pointed out a long time ago. Long time ago. The late 50s and early 60s, when computer science was just being thought of, wondering what the two words meant. We can look at computer phenomena, hardware and software, and for instance, John McCarthy came up with a t-shirt that is the evaluator for Lisp. So this is, and what was fun about it is that in somewhat similar ways to that bridge, this t-shirt is more interesting than Fortran was. Lisp is a much more interesting language than Fortran is, and it suggests many more possibilities, even though it's much tinier. It has all of these wonderful germinative properties. And from that, we can make other programming languages. We can make personal computing. We can make the internet, expanding out in scale. And as we expand out in scale, guess what? We start needing something like the molecular biology of the cell again. So over on the right-hand side, we have things that are kind of math-like. We have bio-like things in real object-oriented languages like Smalltalk, ecology-like things in a personal computing system, and politics-like things out on the internet. Why politics? Because the internet is a communication system, but it doesn't have any particular center to it besides TCP/IP. And what that means is people are going to do things that are going to be quite alien to each other. So Licklider, who was the guy who funded all of this stuff in the 60s, said if we ever, he called this the intergalactic network back then. And they said, well, why do you call it the intergalactic network? And he says, well, because engineers always give you the minimum of what you ask for. And he said, I really do want to have a network that reaches every human being on the planet, so I'm asking for an intergalactic one, figuring that as it goes through the low-pass filter of reality, it will come down from the whole galaxy to at least a tiny little planet like ours. And that's what we gave him. And he pointed out in a memo 50 years ago, in 1963, before all this was done, if we ever succeed in doing an intergalactic network, that our biggest problem is going to be learning how to communicate with aliens. And he meant people. There are going to be people on this who will have different cultures. They won't be like us. He meant software. There's going to be software on machine over here that we'd like to use, but we can't understand it. And he meant software to software. That here's a module over here that might be able to use functionality of this module over here, but their APIs are incompatible. They have no idea what to do with it. So you get all of this, as you go up in scale, you get to something where you really get to an area where negotiation is the kind of level of coordination we should be thinking about. Whereas over here, we're thinking about things that are like predicates. So what we're doing is a combination of things. I'm not talking about user interface today, but that's the theater part. So we've got math, we've got science, we've got engineering, and we also have to do some theater if anybody's ever going to use any of this stuff. So the books here, the equivalent of the molecular biology of the cell, there really isn't one. This one is a good one to read. Classic book from the 60s by Christopher Alexander. An architect. Fred Brooks just wrote a book called The Design of Design. Has a few interesting thoughts from somebody who's done a lot of software systems. Sifakis, I just heard a good talk from him in Heidelberg a month ago. He just wrote a book called Rigorous Systems Design. It's not clear how well his ideas scale, but it's worthwhile looking at. And here's my remedy. What I used to do at Xerox PARC whenever I had a question about systems and stuff, I'd go walking down the hall and I'd ask Butler Lamson, who was and is one of the great systems designers of our time. He's now at MIT and still full of great ideas about how to deal with complexity. And as we'll see later, we'd love to be able to put Butler in a box somehow, because it's this kind of wisdom that we often have to fall back on because we don't really have a great science of system design yet. Okay, another problem we have is that human beings genetically love tactics much more than strategies. So we're basically tactical creatures, and so when given something like a brick, we notice that they can be piled and stacked, and scaling them out, we get pyramids and walls. And that's what we did for a long, long time, thousands of years. We rarely think about things strategically, and in fact, it's almost an accident that the arch actually got invented. So just pause for a second. You can think about the improbability of inventing an arch if you didn't know one in the first place, because to build one, you have to have more structure than is there when you remain, right? You have to make something that's going to hold it up until you get the keystone in place. And so it was somewhat unobvious, and if somebody's interested in asking a question later on, I can tell you where the arch actually came from. But the things you can build with arches are quite incredible compared to what you can get away with bricks, and it's not just having less material. This aqueduct was attempted to be destroyed many times by the Goths and the Visigoths after Rome fell. In fact, the legends of the frost giants that you find in the Wagnerian ring operas came from this. The Goths and the Visigoths concluded that only giants could have built these things because they were unable to tear them down. And what they didn't realize was, it was just ordinary people like them who built it, but ordinary people who had knowledge and technique. The Goths and the Visigoths were just aggressive. That's not enough to tear down something like that. The other thing, again, somebody's interested, the Romans had by far the best cement that the world has ever known, even including today. And this is why if you go to Europe, go to a place like Merida in Spain, there's a bridge there that's been in constant use for more than 2,000 years, and it looks like it was made yesterday. The Romans did not fool around. Okay, so tinkering tactically, that's our normal mode. Computing is rife with it. Tinkering strategically, we hardly ever do. And part of it is because the funding for most projects in computing rarely includes funding for problem finding. Right? Usually the funding comes down with, here's our goal, here's our problem, solve the problem. That's usually bullshit. And the reason is that people who are good at gathering money for funding rarely have the time to think up good goals. It just doesn't work that way. So you're much better off setting a vision of a desirable future and then getting the best people in the world to try and figure out what the problem actually is. This is how we got personal computing and the internet today. So if we look at the spectrum between a CPU on the one side and the project we want on the other, we've got a lot of different ways of writing code. We can write machine code, so it might be billions of lines in machine code, hundreds of millions in C, millions in some other language, hundreds of thousands. Now, of course, we'd love to stay away from the gears. One way of thinking about the change in architecture is we're going to go from gears to biology somehow. And in theory, as we come down working on the very same problem where we only have to do a few thousands of lines of code to realize our project, the programming effort should actually be much less. It should be much, much less. But what we have to pay ahead of time is the inventive effort to invent these higher level languages and forms of expression and architectures that are going to pay off for us. And I think everybody realizes that for large projects today, we're still stuck down here in languages that are rather like languages from the 60s. For instance, C is rather like ALGOL, and itself came about around 1970, 71 or so from a language called BCPL that was done earlier. And so from there, we're just sort of stuck. Simula came about in 1964 or 65 or so, and it was the actual model that Bjarne took to make C++ from. He did to C what Simula did to ALGOL to bring it about. And so we're looking at, in most cases, maybe we add on a garbage collector for Java, but we're looking at programming styles that go back almost 50 years. And people are embedded in them. We'd like to be at the thousands, but the problem with this is it's actually difficult, costs money to do these higher level forms, and there isn't a lot of funding. Like NSF hates to fund these. And who else is going to fund them? Qualcomm? This is a lot of effort. You have to have special people to do it. And so what happens is, except in a few exceptional cases, this level, which should be really beneficial over the long run, particularly in life cycle maintenance of complicated systems, actually just doesn't happen. So this came out of I once consulted for State Farm, and they asked me what I thought of them after I'd been there a couple of years trying to help them. And I said, well, you know these old clipper ships, the old windjammers? And this happens to be the Peking, which I'm putting up there because my uncle actually crewed on the last big voyage of this ship in 1929. No engine. How big was this? It's 380 feet long. So longer than a soccer pitch. The masts are 170 feet high, so 17-story building. This could stay out for a year and a half to 2 years, completely independent. They even raised vegetables on board. They had spare masts running down. This was kick-ass stuff. 1,000 lines. You had to know where they were in the dark to deal with this. And on a clipper ship, so even a relatively small clipper ship had about 100 crew, all superbly trained and could do anything, whether it was light or dark or in a hurricane or not. And that whole idea of doing things has been carried forward, for instance, in the American Navy. So if you take a look at a nuclear submarine or any other Navy vessel, it's very similar. Highly trained crew that coordinates. So a nuclear submarine, about the same size, a little bit smaller than the Peking. It's about 130 crew. That's a lot of people. And so the question is, so we should be asking, do we really need to have 130 crew? Is that even efficient? Is it the best way to run things, particularly when things are going wrong. And so another answer is something that is the same size as both of these has. So basically, the Airbus 800 and the biggest 747 can be flown by 2 people. And if you're going to do a really long one, you have 4 because let 2 of them sleep while the other ones are flying the plane. And how can that be? Well, the answer is you just can't have a crew of 130 if you're going to be in the airplane business, right? So the problem is you can have a crew of 130 if you're in the submarine business, whether it's a good idea or not. And I'm just putting this out there to get to think about maybe these large programming crews that we have are actually go back to the days of machine code when there was so much more code to be written and etc. But it might not have any place today, because today, let's face it, we should be just programming in terms of specifications or requirements. It's a hard job to come up with requirements. And most requirements, most specifications are not runnable and debuggable. Right? So who even knows that the requirements are consistent? So the first thing we need are specs and requirements that are consistent. The way we find out they're consistent are they're debuggable. And if they're debuggable, then it means we should be able to make a prototype using a supercomputer. And if we could actually make a version of the supercomputer, we might be able to ship the prototype. I'm going to come back to this idea, but I just want to get you to think about how many people do you actually need. And I claim, well, maybe what we should be thinking about is what we need is the number of people it takes to actually put together a picture of what the actual goals and requirements of this system are from the vision that led to the desire to do the system in the first place. So now, I went to the internet to find a physician heal thyself, which I knew I would. Anybody know where it comes from? That line? No, Bible. The Bible. So John, Gospel of John. But I didn't expect to find a T-shirt with "Physician, heal thyself" on it. But I'm talking in terms of T-shirts here. And by God, Google came up with a T-shirt for this slide. That's what we should. Why did I say that? Well, remember, we're doing systems for everybody else. Computing has been terrible the last 30 years in doing systems for itself. Right? We should be able to make better languages, better in development environments, and yet most computer people use vendor stuff as though it's not important, as though we should be able to put together thousands of people working our asses off on inadequate tools and weak expressiveness. So anyway, so let's put that aside and go back in history 50 years and take a look at one of the earliest interactive systems ever done. And this, in fact, was the invention of computer graphics, interactive computer graphics. And I've got a little movie here that I'll play for you so you can see what it actually looked like 50 years ago. So he grabs some ink, and he wants a rivet, but he's not trying very hard because he puts a little center of that arc there because the system will solve problems for him. So he's pointing to the edges here, and he says to Sketchpad, make those all mutually perpendicular, and there's Sketchpad solving that problem. Right? So this is the system in which you program with constraints. You program with the things that must be true in order to satisfy what you're trying to do. No sequential coding here. Here's another solution to that problem. And he could constrain the ratios of things and so forth. So that's one hugely powerful idea done on a machine much, much larger than this room. And that happens to be a master of a rivet. And now he's going to get an instance of a rivet. And we would call the master a class because this is the first system to have real objects. So this is just an instance of the rivet. He's showing he has little knobs that he can use to rotate the rivet and make it larger and smaller. He's now going to... Now you might ask, why is the display twinkling? The answer is it's not really display. It's just a point plotting oscilloscope because Ivan Sutherland had to write the display code. He had to make a display. About half of this supercomputer back in '62 was used just to do. So now he's showing you, I can make different instances of the rivet, but he forgot about these cross-hatching, so he says, let's make those transparent in the master, and now when we look at the drawing, all of the instances have felt that. And then the last little trick here is he's going to show you zooming and clipping. So the drawing that he's working on is about 1/3 of a mile on the side, the virtual paper here. And he can make anything that he constructs into a master. And he just did that with the rivet and the flange. And here's an instance of that. Here's another instance of it. And in fact, all of the letters and numbers in the system are done that way as well. So the whole system is made of a few simple ideas that are extended out in a most general fashion. So we have interactive computer graphics itself. We've got masters and instances, the object idea. We have programming in terms of constraints. And the examples I've been showing up on the board here are this interesting thing that Sketchpad had in that you could construct bridges and electric circuits without the system knowing about these ahead of time. So how would you do a bridge? Well, a bridge is actually made out of beams. The beams are actually like very stiff springs. And so if you told Sketchpad to try to maintain the length of these things and just built a bridge-like structure from them and turned on the constraint mechanism, you will get something like a spring system that's trying to get itself into equilibrium. There are no movies of this because the supercomputer in 1962 was too slow. It took about 30 seconds for frame time. And so to honor this, several in our group, Yoshiki Oshima and Bert Freudenberg, we made a recreation of the Sketchpad bridge here just to celebrate. That's fun to be able to do it on a laptop. So basic idea, yeah, you can just hook things in here. We can turn gravity on. We can hook in a weight here. Now if we let it settle, it looks like it's actually all settled out there, but if I turn on the decimal points, we can see that it's still wiggling. Right, because nothing physical is ever really still. And I can tie on another weight, and we can take a look and see what happens to the stresses and strains around here when I put in this last beam here. Okay, so that's awfully cool. Be nice to have something like that today. It's that neat and easy. And of course it solves nonlinear problems, so it goes far beyond what a spreadsheet can do. And one of the things that we tend to do in computing is when we have a hard time working on the real problem, we do other things. So the other thing here was, well, at least we can make a better display. So there have been generations of better display. So here's the same simulation here in modern terms, and a few little wrinkles here, so I can type. So words have weight here. and so forth. And just to show you the three rules here, so we use a slightly different version of the constraints, but these are the three constraints that this system actually uses. The top one is gravity. And so if we release gravity here, what we hope that everything settles down to zero. It's just being pulled by the springs into equilibrium. So I put gravity back on. And the middle one is the spring constant. But the bottom one is kind of interesting because it's the one that governs the pins. So the girders are all hooked together with pins. And so let's see if we turn off the pin constraint. See what? Okay, so the whole thing comes apart. Gravity is still working, so they're all down there. And this reminds us that what we're always looking at are kind of a costume show. Right? What we're seeing is costumes, and we can repurpose those costumes into, for instance, the user interface of this system I'm using to give the presentation. I'm obviously not using PowerPoint here, right? So this is a time for a philosophical pause. It's like, why would anybody use PowerPoint ever? Why would any computer person ever use PowerPoint for anything? The whole point of the thing is not to simulate old media, simulate acetate slides. The point is to use the fact that the computer is a simulator. So this steel look, which we got from the girders, that looks a little too Microsoft-like, so I will go to this Halloween theme, which is perfect for tomorrow, right? And this system here is called Frank, the little Frankenstein monster here, because it is a collection of different experiments that we did to try and explore this question of how complicated is personal computing anyway. And of course, part of the what you might call the ethic of doing something like this is, well, we should at least be able to give a presentation, make a media system in the very thing that we've done for experiments. So we have a bunch of systems here that computers are ideally suited to help us understand. We have natural systems, we have social systems, we have technological systems, and we are a bunch of systems. Those are four really important systems that computers can help us understand. Now, to our little science project here, one of the questions we had is, well, if we're going to think of these t-shirts, this metaphor that I've been showing you about personal computing, how many t-shirts would it take to do what I just showed you? But we don't know how to do it with one t-shirts with math. Wouldn't it be great to have something like the equivalent of Schrödinger's wave equation and just have a personal computing system materialize? So we can't do that. But when we look at all of the things that we have to do, it seems like a lot. Here's another view of it from the end user to the CPU. Maybe more than 100 million lines of stuff. Lots of different kinds of things. And so the way we thought about doing this is to try and take each kind of thing and see if we could come up with a way of expressing it. So this is what you might call a DSL approach. And except each one of these DSLs is actually a full-fledged language. And I'm not going to talk about all of these, but I'm just pointing out these are a couple of, maybe a dozen or so arches that we identified that could be helpful in doing this. I'm going to say a little bit about the math wins one, maybe a little bit about no centers, a little bit about loose coupling, t-shirt programming, and maybe particles and fields. We'll see how much time we have here. And there are more. So these are Some of these have been around for quite a while. And here's the problem. The present is so vivid that it makes it difficult for us to see anything else. Because as McLuhan pointed out, most people can only experience the present in terms of the past. So when we're in the present, we're not only experiencing things in terms of the past, but the past that we can see is most vivid because it contributed to now. But the past is a lot larger than that. But the problem is that if we're hooked on the present, as most people are, then most of our images of the future are incremental to the present. And certainly computing has been mired in that for the last 30 years. So you want to find a way of somehow suppressing the present. And I don't have time to talk about it now, but I will talk about it a little bit this afternoon if people are interested in ways that you can suppress the present. If you suppress the present, that allows you to suppress the past that led to the present. It allows you to see other things that are in the past that were masked by it, and allows you to possibly come up with a very different way of looking at the future. And that's kind of what we did here. Virtually all of the principles that we used in doing this experiment already existed. They just weren't being used in computing. They're ones that, as an example, one of the ideas, actually a bad idea that won out, was the semaphore. But it actually became very popular in the 60s, and it's been taught every generation since then. Why are semaphores a bad idea? Because you can get system lockup. And a much better idea, called pseudo-time, was invented about the same time as the semaphore, but it was not invented by a person who was held in as high favor as the people who came up with the idea of the semaphore. And so that idea just never got used over the last 50 years, in spite of the fact that it's a superior idea. So that's an example of just picking up one of these ideas from the past that got discarded for no particular good reason. So I'm going to go through a couple of these systems. One is, how do we do the graphics in this system, because that's a huge area of its own. And actually, I'd like to introduce Dan Amelang here, who actually did this work. So you can ask him questions about it. He's actually supposed to be writing his thesis right at this very moment at UC San Diego. But since this is close, he came over. I'm going to take advantage of semi-shaming him into thinking. He's actually done 2 PhDs worth of work on this stuff. So if you think about what is graphics on a personal computer, it's a lot of different things. It's rendering, it's anti-aliasing, it's compositing, it's making various special effects and so forth. And so typical packages are like the one in Firefox, might be 500,000 lines to 1 million lines of code. Microsoft's version of this is even larger. The browser has many different forms, unfortunately, of trying to do a range of computer graphics. So the idea here is it's no fun if we don't cover the entire space, right? So the way to actually make the point in this experiment is actually to do all of the 2.5D computer graphics that are commonly used in personal computing. And so the first thing that Dan looked at was this question of arbitrary shapes with pixels, and he came up with a new way of defining what that means more or less directly. That is a formula that will actually compute the shading that has to go into an individual pixel without having to do super sampling and so forth. So that was new. But that formula doesn't run unless you have an infinitely fast computer. And so his real task was to make a language that was like the mathematics of that formula that you could run on a computer. And so here's 45 lines of code that does the involvement of an arbitrary shape with an arbitrary pixel. And that code is actually runnable. And it does these kinds of things. Makes characters and fills shapes. And one of our researchers, the wonderful Brett Victor, user interface guy got very interested in trying to make this a little bit more understandable. And he used the fact that Nile is a data flow language and the code is very small for doing this. And so he came up with a visualizer that looks kind of like this. So here's live code as I move around here, and I'm going to change this D into a kind of a B, just so you can see I can edit it. Okay, and then what Brett has done is automatically taking this code here, these are the code to do this chain, and fixed it so that if I want to know where a pixel comes from here, I click on this. If I want to know where this line goes, if I want to know where these 6 raster elements go, notice I'm scanning down here, where the span coverages go and so forth, that it comes out automatically from this code. And I can expand. Here's a Nile routine that says to make a texture, I have to expand the spans, I have to duplicate, I have to make a linear gradient, I have to go to the pad gradient, gradient span, and so forth. You see these little arrows here, gives a pipeline. And so if I expand this, here is showing, again, if I go here, here's the expand spans guy, the linear gradient guy, pad gradient, gradient span, and so forth. So the point here, besides the fact that this is neat and it was done automatically, is if you're going to do DSLs, you not only have to do the DSL in a timely fashion, and it has to run fast enough to be interesting, but you actually have to have a way of debugging and understanding it that doesn't require a couple of years' experience. And so the whole human experience is actually part of this idea. Now there's more to that because we have compositing. So we've got compositing that's over. We have compositing that involves alpha blending like this. And these are all of the compositing routines here. They're all about a line long that are used in personal computing. In fact, what's fun about these is that these are the math that are actually written when you read an explanation of how thousands of lines of code do X, Y, and Z. But in this case, the math actually runs and it actually does the computation. So all the compositing rules are about 95 lines of code. Then there's pen stroking. So pen stroking is like this. There's texturing, which we just talked about, gradients and other kinds of things. A good way of illustrating that is to go back into the user interface here, and I'm going to pick a user interface element like this one. This guy is active, but I can also change it while it's running. So I'll just select it, and here I'm going to pick a command called gradient fill. And while the system is running, I can actually make the changes here to get it to be a little bit more the way where I want it, like that. Okay, so that's 71 lines of code to do those. Gaussian filters, for instance, for nice shadows, diffuse shadows, and so forth. And the whole total here for the whole graphics system of the graphics you use on your personal computer is 435 lines of code. That is something that is very, very close to and this is counting the fact that, for instance, this guy, composite, is written in 3 lines of code rather than 1 line of code. Right? So what we're saying is that it is possible to take something that is essentially the complexity of doing this graphics and to write it without any complications and come up with something that is incredibly small, like a factor of 1,000 smaller, more than a factor of 1,000 smaller than writing it in C or C++. And in fact, this code is running right now. It is the code that is running to do my presentation. Thanks, Dan. Now, if you just write that up, goddammit, we'll give you a PhD. Yeah, I mean, and I'm really glad you applauded that because this is really great work. Absolutely great work, and in many ways, it's the poster child of this project. No. Yeah, I'm going to show you what else had to be done. I'm glad you asked that question because, of course, 435 lines is not the only thing there. It really doesn't count if the 435 lines are somehow using some Mac. Yeah, so the answer is no. Because otherwise it would be kind of like kissing your sister. And this is much better than... Yeah, so between this very high level up there and the result, some compositing there, there's a whole bunch of stuff. And we have to somehow do that, or else we're not going to get the thing working. So I'm just showing, I'm not even going to bother mentioning, there's just different boxes that have to do things. Here's a 86 CPU, we have to do something for other CPUs, and there are all these transformations and blah, blah, blah. So right away, we're either going to spend a lot, we're going to use up our code budget doing this, or we have to have another one of these special languages. And so here's one that Alex Worth did, and it's a little bit like a meta compiler, but it actually deals with any form of structured objects. So it's something that not only can do the parsing stuff, but can also do transformations, to do optimizations and other kinds. Sort of a general pattern matcher and transformer. And so here it is doing something. I'll get a more complicated guy here. So like the simplest thing is something like a BNF grammar, and it will make trees, but I can also feed the trees into these guys. And so does that help? And the answer, yeah. So to make Nile, it takes 130 lines of this special meta language, and to make it run fast enough, it takes about 700 or 800 lines of this thing as an optimizer to organize things so that it can be run rapidly. And you can see at the top we have a variety of different outputs where we can generate to JavaScript, C, we can generate machine code and so forth. But, right, now I've got this meta language. So I have to make that. And that's where things get to be fun because, remember, the meta language is a language for making languages. So to make it itself, it's 76 lines of code plus another 30 or so for optimizing it. And now we've closed that circle. So we use that for making all of the little languages there. So it's not 435 lines of code. It's 435 plus making the language itself plus making the language that makes the language. But we can amortize what it cost us to make the language because we're using it for other languages as well. So this is the way the game is actually played. Okay, here's another example. Something standard that you have to do is TCP/IP. And here we have something actually different. TCP/IP was invented by experts, and most of the TCP/IPs that are around were programmed by experts, unlike most code. So the question is, what is the wiggle room in something done by experts? So here's the state diagram, and here's typical C version of TCP/IP is about 20,000 lines of code. So that's a lot for these demonstration purposes. And I should mention that there have been, for instance, a number of Scandinavians have done really good versions of this in about 2,000 lines of code. So there's wiggle room there of about a factor of 10. We took a different look at it. We thought about it, well, instead of a state diagram, we could think of TCP/IP as kind of like a non-deterministic parser. Right? If you turn your head around and realize, well, there's stuff streaming in from the internet and it's not always in order and there are errors. And so it's rather like, and we have to recognize the structures that are there. We have to put them in order. So it's actually a bit like parsing and reconstruction. And so Ian Piamarta did something that is, now this is a crowded t-shirt because it has 3 pages. So it's about 160 lines of code to do a version of TCP/IP that will run a website, right? So there's not as much wiggle room there. Probably the most you could get, I think this can be made a factor of 2 smaller, and I think it could be made nicer. But basically, on code done by real experts that is not too large, you can still expect to get between a factor of 50 and a factor of 100 by looking more closely and using a higher level form in which to do it. Okay, so this one is a facetious project, but I just want to show you because you can have fun with this stuff also. So ants, here's what ants do. When they run into food, they pick up the food and head to the nest, and they lay a scent trail. And when an ant without food runs into the scent trail, it uses it to follow a gradient upstream to find the food more efficiently. And you notice now almost all the ants have been organized, even though they're not communicating with each other. So you can think of this as making something like a chemical magnetic field that is organizing particles. And so that got us to think about this image here. That, wow, those little text characters, they just do look like ants. And so if you thought of each one of those as a separate little ant, and the question is what conditions could you put out around them so they would organize themselves into a little text justifier and editor. And the simplest one is just follow the leader. If you don't have a leader, go up to the upper left-hand corner. And if you're over the margin, tell the guy in front of you and so forth. Here's a simpler one. Wait till the guy in front of you goes and then jump. And if you do that in between frame times and your parallel processing is working nicely, you're going to get something that is very, very like what you spend much more time on trying to do as a sequential algorithm with backups and everything else like that. So this again is now I don't have time to actually go through this. I'll just point out that this, what we have here is a document in this system, and it's actually an essay containing code. So I'll show you the first part that explains how to actually write this code. So here's the code, and so the first 2 guys just disperse the text, and this next guy follows the leader, but they don't know how to wrap around, and so on and so forth. So this is all of the code in the system here for doing this, and finally we get that. So this is just pointing out that taking a different point of view, especially a highly parallel one when you have multiple entities, and especially when you have objects instead of data structures, winds up with a very different way of thinking about the code. Okay, so now up into this, we're getting into the system area here. So we think about computations as being intercommunicating processes. That's an old idea. And we can imagine that on one of these processes there's a user interface so we can see what the computation is actually doing. That's kind of what I've got here. And suitably organized, that computation of virtual machines should map over physical machines. And it should map in more than one way. So for instance, if you're doing mobile computing, you might have less in the place where the user interface is and more out in the net. So these guys should be migratory. And this has actually been done in the past, but it's not actually done very routinely in standard computation yet. And so you wind up with something that looks like a recursive version of the internet. You've got machine processors that are kind of like an internet, physically hooked together, and then you have virtual machines that are virtually hooked together using loose coupling. And so the way to actually do this is to think about next generation publish and subscribe. But you need to do it semantically because now we're talking about the entire internet. So we can imagine each object here has two bulletin boards, or you can think of them as broadcasts, sending messages to nobody. Here's what I need and here's what I produce. And in the size of the internet, we're going to need negotiation processes that help deal with the differences between the superficial differences between these objects. And so, for example, in fact, this guy does produce what this guy needs. It's not in the same terms exactly, but I know how to reconcile those terms. That's a negotiation. And this guy gets his needs from somewhere else. This guy, what he produces goes somewhere else. And so you wind up with a kind of an object-oriented system in which messages are only received. Something to think about. Right? It's sending messages that is actually the problem in scaling. Because who are you going to send them to? But receiving is a perfectly good idea. So this idea that goes back to Linda, but actually needs semantics rather than syntax to work, is going to be a hot area over the next 5 to 10 years. And the last idea here is what does this look like in an actual system? And this kind of came a bit after the fact here. So here's a document. It's active. So for instance, I can grab onto these histogram guys, and that pink line there is the average. And here I have things like spreadsheet cells in the object. And all of these things are hooked together in this system by this loose coupling that I was talking about. And we put in a bit of a hack, admittedly, to make these loose couplings visible. Here they are. So this is finding, and so these are not explicit bindings, but actually dynamic bindings. And when something gets sent between them, they will light up. So as I move this guy, you can see the things lighting up. Now this is only for illustration purposes to give you an idea of what lies behind this system. Okay, and then here's what I think is going to happen in the future. Here's what we have been doing. We've been doing things that are basically solvers. We've been doing how things get done using armies of programmers. We've written compilers. We've done every kind of thing down here. But just as in Sketchpad, what we really want to deal with is the what's, the constraints, the meanings, the relationship, going back into time, as McCarthy, Sutherland, and Ed Feigenbaum talked about. And so we want this stuff to not be touched by human hands anymore. We want to think about this as an You can think of it as automatic libraries. And how do we find the libraries? Well, we need something like Butler in a box. In other words, we need an expert system that knows the heuristics of systems design, and from things that are much more like specifications, it can make the choices like a compiler, but now it's a semantic compiler, to dip into all the different ways we have of solving things to make something that's not just machine code, but an organization of solvers. This is something we can talk about this afternoon if people are interested. And here is Alan Borning and Hessam Samini, who at Viewpoints are working on this problem. So I guess the punchline for this talk is everybody is familiar now with 3D printing. And the way that I think about 3D printing is the work we want to do when we're dealing with artifacts is, that's a nice one, a whole car done by 3D printing. Here's a flute that actually plays well. What we want to do is do the design work and have all the other stuff be automatic. In other words, we want to ship the design. Now in computing, we have n-dimensional printing, right? What we're printing is actually relationships in n space that are dynamic. So it's slightly more complicated than some of the things in the physical world, but it's the same idea. In other words, our development systems should be like CAD systems. We should be able to do every phase of design and every phase of testing and every phase of simulation in that design system. And then the optimization parts of it that allow, and this would be done in using a supercomputer, what used to be called a workstation. It's interesting that workstations aren't around anymore because people think these machines are good enough, but they aren't. So whenever I go to a research center and I see people using laptops, I really worry because you're computing in the past with a laptop. The way to compute in the future is to compute on something that's about 50 times the power of standard computing today, and that allows you to actually test out these prototypes and think about shipping the design. So I'm going to quit there. We've got time for a few questions, and then we have this session in the afternoon. Thank you very much, and please ask. Don't bother applauding. Just to ask questions because time is precious.
Please wait for the microphone if you have a question.
Yes, by the way, anybody who feels like leaving, please do. Quickly. Yes.
Your language Ometa, is that available for people to play with?
Yes, yeah. Yeah, and there's a thesis at UCLA from 2007. Oh, he's asking about Ometa. When did Alex do that? Yeah, it's like 2007 or 2008. And there is a very nice version to play with that I mentioned that outputs to a variety of things. And there's a version that you can just run in your browser. You can just go to a URL and it will download in your browser, and and it comes with maybe 20 languages that have been made in it. So you can sort of see how a language is made, and you can make languages yourself to just get started.
Yeah, thank you.
Yeah.
Yeah, you mentioned specification, and from the specification, the generation of code, right? And there were attempts,
Well, I meant I think I said generation of behavior. Yeah.
Yeah. Okay. There were some attempts in the 70s to create specification languages that would actually automatically be, compilable to C or some other high-level language. Mm-hmm. So can you comment on
Well,
this?
C is a low-level language. I hate to tell you. It's really low. Yes, well, every decade. So one of the most interesting things, one of the reasons I showed Sketchpad, besides the fact that I love that love to show people that demo. Most people are not aware of just how sophisticated the thinking was 50 years ago. Meaning a lot more sophisticated than a lot of thinking is today. So if you think of that as being the work of one person in 1 year, and there was nothing like any of those three things done beforehand, that's what I call a real PhD thesis. Right? So, yes, every decade, the whole point of higher level languages was the languages were not called DSLs back then, they were called POLs, problem-oriented languages. That's what ALGOL was. PL1 was supposed to be a problem-oriented language. COBOL was a problem-oriented language. So the idea was to try and match up in some way to the general problem domain in such a way to cut down the gratuitous stuff you had to write in order to make desired things happen. And yeah, it's a hard problem. But the fact that it's a hard problem shouldn't dissuade people from working on it. The real question about any problem is not how hard it is, but how worthwhile a solution would be. And this is what has been lost, in my old fogey opinion. People, it's like AI. People are doing AI in a very incremental fashion now because they got discouraged and they're only getting rewarded for success, not for good efforts. So the reward system is very tough in all of these areas. And to do a programming language that's actually usable, like Nile. Nile is interesting because what was needed for a thesis was done very early. But when we decided, the problem was that he did it well enough so that even the first versions ran almost in real time. And that got us to be tempted to actually use it. But then there was an enormous amount of work to actually do all of the things that you have to do behind the scenes to go from a demo to something that you can actually press into service and have somebody like me be willing to actually run long lectures just using the thesis tool. So yeah, it's a problem. And it's not that Moore's law gives you the solution automatically. Right? Just having more capacity and so forth doesn't do it automatically. On the other hand, it does make a huge difference. For these systems, for instance, just in optimizing compiling, the way compilers used to have to be optimized could not use enormous stretches of code to do it. But in fact, some of the best optimizers that have been done in the last 10 years do exactly the opposite of what was good practice 30 years ago, because there's tons of memory. And so there's no reason not to do what's called a tracing optimizer, which is you just have a thing that is capturing the code that's executed from an interpreter and encapsulating long stretches of this code and weeding it out and just snapping it in there as long routines. So you get a just-in-time compiler that starts rivaling what you can do in C, even in a language that doesn't have static types. So each era gives us a different set of possibilities. But I gave this talk in part to illustrate that these problems were articulable and were articulated 50 years ago. And computing itself has done a very poor job to 50 years later be still programming in something that is roughly a mid-60s kind of language like C, and produce these mountains of code. And by the way, 85% of the cost of any major software system in industry is incurred after the application has been successfully deployed. So the costs from these immense mountains of code are partly in not just maintenance, but the fact that the requirements change. And it's very, very difficult to have this code be anything remotely flexible in the forms that they're written today. So this is just wrong. Down here, yes.
So you came up with the Dynapad.
Dynabook,
which is, yes, I'm sorry.
Yeah.
Which is mostly, we've got iPads and all these
Yeah.
tablet computers now, but does it tick you off that we can't even run Squeak on it now?
Well, you can.
Yeah, but you got to pay Apple $100 just to get
Well,
a developer license.
Well, there's a variety of things. I'll tell you what does tick me off, though. Basically two things. The number one thing is, yeah, you can run Squeak and you can run the eToys version of Squeak on it, so children can do things. But Apple absolutely forbids any child from putting a creation of theirs to the internet, and forbids any other child in the world from downloading that creation. That couldn't be more anti-personal computing if you tried. That's what ticks me off. Then the lesser thing is that the user interface on the iPad is so bad, because they went for the lowest common denominator, and I actually have a nice slide for that, which shows a 2-year-old kid using an iPad and an 85-year-old lady using an iPad, and then the next thing shows both of them in walkers, because that's what Apple has catered to. They've catered to the absolute extreme. But in between, people, when you're 2 or 3, you start using crayons, you start using tools, and yeah, you can buy a capacitive pen for the iPad, but where do you put it? So there's no place on the iPad for putting that capacitive pen. And so Apple, in spite of the fact of making a pretty good touch-sensitive Surface, absolutely has no thought of selling to anybody who wants to learn something on it. And again, who cares? There's nothing wrong with having something that is brain dead and only shows ordinary media. The problem is that people don't know it's brain dead. And so it's actually replacing computers that can actually do more for children. And that's, to me, that's anti-ethical. Right? So it's... My favorite story in the Bible is the one of Esau. Esau came back from hunting, and his brother Joseph was cooking up a pot of soup. And Esau said, "I'm hungry, I'd like a cup of soup." And Joseph said, "Well, I'll give it to you for your birthright." And Esau was hungry, so he said, "Okay." That's humanity, because we're constantly giving up what's most important just for mere convenience and not realizing what the actual cost is. And so you could blame the schools. I really blame Apple because they know what they're doing. And I blame the schools because they haven't taken the trouble to know what they're doing over the last 30 years. But I blame Apple more for that. I spent a lot of, just to get things like Squeak running and other systems like Scratch running on it. Took many phone calls between me and Steve before he died. I spent, he and I used to talk on the phone about once a month, and I spent and it was clear he was not in control of the company anymore. So he got one little lightning bolt down to allow people to put interpreters on, but not enough to allow interpretations to be shared over the internet. So people do crazy things like attaching things into mail. But that's not the same as finding something by a search in a web browser. So I think it's just completely messed up. It's the world that we're in. It's a consumer world where the consumers are thought of as serfs and only good enough to provide money, not good enough to learn anything worthwhile.
Alan, I have a question online.
Yeah.
At Qualcomm, we work on low-power embedded systems with significantly less processing power than a workstation or desktop computer would have. So wouldn't operating systems such as a high level of abstraction result in suboptimal code once it's translated through abstraction layers that wouldn't run well in such a tightly constrained system?
Yeah, it's an interesting question. This is one of these interesting... So an interesting thing about computing is there are first-order theories and second-order theories. Like a first-order theory is you should never do your own operating system or your own programming language, right? Because that could be a black hole you'll never get out of. Years later, you might have forgotten what you originally did that operating system for. But the second-order theory is if you're skilled enough to do your own programming language or your own operating system, you should. Because now you're not working around vendors. Now you're not dealing with anybody's ideas except your own, and so forth. So the the way I would try and answer that question is to take a shot at it. Because the big problem with computing is we can't prove things the way we do in math. Almost nothing that can be proven in computing is interesting. Right? So we're forced to the much harder thing of having to implement and then debug what we implement, and then we can assess how good an idea is. So what I would do is put 5 smart people on that question. It's only 5 people. Find the smartest ones you can, and I would guess the chances are 90% that they would prove the supposition wrong. That they absolutely could turn out something that rivals what is done by hand and rivals it in more than speed, rivals it in actual speed to completion, speed to something that is actually shippable. Because there's nothing slower than a system that isn't debugged yet, right? As far as the end users are concerned. Essentially, so the question is, what is the entire, it's like integer benchmarks. People used to get on Smalltalk for years because it had slow integer benchmarks. Fact is, it was faster than C++ at the user level. Because as a system, it was much more efficient. And the integer benchmarks didn't mean anything. Right? So you have to understand what it is that you're measuring. And so when we were benchmarking processors for a forerunner of the iPad at HP, instead of doing simple benchmarks, what we did is, because Squeak Smalltalk can be bootstrapped in a day or two by somebody who knows how to do it, we just put Squeak Smalltalk, the entire system, on every one of these processors. And then we could run real programs at the user level and see what the actual ups and downs were of these processors, rather than taking a look at something that might not be significant, like some cache speed for simple operations, but maybe there's memory blockages for more complicated ones.
Any last questions? One time for
yes,
one
sir.
more.
He's going to...
So I really enjoyed your talk. The question is that I see a lot of the ideas you're kind of presenting sort of in a software context, and you kind of chastise the last 50 years of software for their progression, but how do you see things happening in hardware? Because the same concepts can be applied to hardware design. So things like high-level synthesis, et cetera, how do you think they're doing in relation to the progression of software design?
Well, I think, so there's two, I mean, roughly speaking, you can think of commercial hardware versus hardware. So for instance, Intel does not really have a huge incentive to do better. You know, they're a company, they're making money. They've leveraged a similar architecture for a long, long time, and as far as I know, nobody's really complaining. They should. But I consulted for Intel for a year, and it's, you know, the problem is sort of, unless you can get the Christian Scientist to actually realize the gravity of having appendicitis, nothing is going to happen. Right? At some point, something huge enough might get somebody to look at a different way of looking at things. But Intel a long time ago took a little pass at it in the late 70s and early 80s. And some of the same people who worked on that are still at Intel. But the thing is that there's no real pull for Intel to do that. But and also because of, if you can't get the major processor companies to do something like microcode, and of course they do, right? Every processor is loaded with microcode and nanocode to do, because most of them are complex instruction set processors. And those complex instructions are actually little pieces of code in there. It's just that you can't load your own code. The closest you can get is to put something into the Harvard cache that's down there. But in 2007, a knee of the curve was turned in field programmable gate arrays. So the chips, two things happen. One is the chips got enough gates on the field. Everybody know what a field programmable just a bunch of gates. The program is really funny because it's just a string of bits that goes into an extra layer of metallization and has the effect of wiring up all of the gates on the chip. So the two things that happened is enough gates got put on a chip starting in 2007, and then the optimization, which is no trivial thing, to be able to know where these functions that you write in a kind of a programming language, where they're going to be placed on the chip, so you actually get to use a rather large percentage of the gates that are on the chip. Both of those things got solved above a qualitative level around 2007, and then a couple of years later, one of the Xerox PARC guys, Chuck Thacker, put out an equivalent, modern equivalent of what the Xerox PARC machine was like, made out of these things. And it's called the BEE3, and the company is called B-Cube. And it's like $28,000. It fits into a blade slot. It's got 4 of these enormous Xilinx FPGA chips on it. It's got 170 gigabytes of RAM, and it's just loaded to the gills. And as I said, you can put it into a blade slot. So a 5-page program in one of the languages you can use with it, like Verilog, will give you a 300 or 400 processor, 32-bit processor supercomputer just in this box with your own memory architecture, because these are just gates. So you can make the memory, you can get rid of the von Neumann bottleneck by involving the computation next to the memory where things are going to be. You can make it highly parallel, and so forth. And a few universities, UCLA, Jason Kong, MIT, Carnegie Mellon, and a couple of other places are the only ones I know that have graduate courses in how to deal with this technology. But what's nice about it, and you can do all kinds of things. So for instance, if you know how MPEG works, you can make a hardware MPEG thing out of one corner of one of these chips. And it's completely parallel and so forth. So it's really a different way. It's very Xerox PARC-like. A machine we had at Xerox PARC in 1973 had the equivalent of 16 processors microcoded to do everything. And personally, as a systems designer, I think of hardware as just software that's crystallized early. Right? It's just early because it's all process. Hardware and software, those are bad terms because they've led to two different cultures, which was not true in the 60s. In the 60s, in order to get a PhD, you had to be able to do both hardware and software because it was thought of as computer science was the science of processes. And so when you think of the processes that you're going to manifest in order to do what your problem is, at some point you have to think of the hardware thing, and you really don't want to spend 90% of your time dealing with some awful hardware interface. For instance, we can ask Dan. Actually, one of the questions, Dan, was about the extent to which you can use multiple hardware threading and cores and stuff. And I should have mentioned that the Nile system automatically adapts itself to the number of cores and hardware threads that are there. But how much work was it? Yeah, go ahead. Use your mic.
Right. So we have this high-level language now to express computer graphics, and we've been using it for other things too, like cryptography and media decoding. But this is a very high-level language, and the question is, how can we make this run efficiently? And one way we can do that is to automatically parallelize these very high-level programs. And so we do that via automatic SIMD generation. We can also spread it among the cores of your desktop, or we can even spread it among computers. And so, we've put a lot of work into making that happen automatically, resulting in systems that are more efficient than those written by hand in lower-level languages where these things have to be done by hand. And so that kind of goes into the question about how to get efficiency on systems that really need that? Do we have to discard high-level language? And the answer so far is it doesn't look like it.
Yeah, and so the pain level question is it was not trivial to deal with the cache lines in the Intel architecture, because I remember when you were going through that.
Right.
Intel does not make it at all easy to actually make you, because you have to realize the multi-core stuff was a hack by Intel when one of their chips melted down a few years ago, and it surprised them. They were not able to even predict that was going to happen. And what can we do now? Well, we'll just slap multiple cores on a chip, but in an inadequate memory architecture. So it's actually rather difficult to feed even one core from the way that Intel does the memory architecture, much less 4 cores that are doubly threaded. So, but he did it. So I'm just no, I won't even use a biblical thing. Okay, go ahead.
That's fine. Yeah, Alan was just referring to, we're having this discussion about hardware, and so, yeah, I mean, because we don't get to run on our own hardware, then, yeah, getting Nile to run efficiently on the hardware as Intel gives us, yeah, was a lot of work and time, and I kind of wish we had an engineering team to farm that out to. It was harder than I thought, so yeah, I mean, it took a lot of man hours to efficiently spread the computation among Intel processors.
Yeah, originally we were going to do this as a proof of concept using FPGA stuff, but then we got sucked into the lure of giving demos like I gave today, just dragging an ordinary laptop along, and it's a good thing for his thesis because he's actually using hardware that people recognize rather than mysterious hardware that most people haven't really looked into. But however, for practical things, I always believe in you should have the option open for rolling your own hardware, and you should have the tools for actually doing it. Might be just doing ASICs the right way, but just a simple little ASIC that can handle the 3 things that are high overhead in doing a virtual machine would make an enormous difference in a small memory, small processor architecture. Make an enormous difference. Because bytecodes are a lot smaller than regular instructions. So if you can make those run as fast as a regular instruction, you're way ahead of the game. That's another answer to the previous question. It's like keep your options open. Okay? Okay, thank you.